All right, today we are going to demystify the very heart of electricity. We're talking about what it is, what makes it move, and the one single beautiful rule that governs pretty much everything. I mean, seriously, think about it. It's something you do a dozen times a day without a second thought. But behind that simple little flick, there's this incredible, invisible world of physics doing its thing. So what is actually going on in there?
Well, when you flip that switch, you're completing what we call an electric circuit. The best way to think about it is like a racetrack. For anything to happen, you need a few things. A complete, closed path. That's the track itself. You need a power source, like a battery, to get things moving. You need a component, like our light bulb here. And of course, you need the switch, which basically acts as the starting gate.
So, if the circuit is the racetrack, what's actually racing around it? Well, that brings us to our first huge idea: electric current.
Okay, so let's break this down. The textbook definition is the rate of flow of electric charge. Now, the two most important words there are rate and flow. It's not just that charge is moving, it's about how much charge is zipping past a certain point in a specific amount of time.
And you know, physics gives us a really nice, simple formula for this. I equals Q over T. I is the symbol for current, Q is the amount of charge, and T is time. It's really that straightforward. Current is just how much charge flows per second.
So how do we measure this? We use a unit called the ampere, or amp for short. It's named after the French scientist André-Marie Ampère. And 1 amp is super easy to define. It's 1 coulomb of charge flowing past a point every single second. Simple as that.
Okay, but what is a coulomb? Well, get ready for this because this is where the scale just gets mind-bending. 1 single coulomb is the combined charge of about 6 quintillion electrons. That's a 6 with 18 zeros after it. It's an absolutely massive number of tiny particles flowing through that wire every second.
Now, here's a quick heads up on something that trips people up sometimes. Back when electricity was first being studied, scientists just assumed that positive charges were the things moving, from the positive terminal of a battery to the negative one. We call that conventional current. It was only later that we figured out it's actually negatively charged electrons flowing the other way. So even though most circuit diagrams you'll see still use that old convention, it's really good to remember what's physically happening inside the wire.
So, we have all these charges just waiting in the wire, ready to go. But they don't just move on their own. They need a nudge, a push, and that push is the next major piece of our puzzle: potential difference.
The best way to get your head around this is with a simple water pipe analogy. Imagine you've got water in a pipe that's lying perfectly flat on the ground. The water's just going to sit there, right? It's not going anywhere. But the second you lift one end up, you create a pressure difference, and gravity immediately makes that water flow downhill. And believe it or not, that's almost exactly what's happening in an electric circuit. The charges in the wire are like that water in the flat pipe. They need a push, and the battery provides that push. It creates what you can think of as an electric pressure difference, and that is what we call potential difference. It forces those charges to start flowing.
So when you get right down to it, potential difference is all about energy. The official definition is that it's the work done, or the energy you have to spend, to move a charge from one point to another. It's basically a measure of how much energy each little packet of charge gets.
And again, the formula is beautifully simple. V equals W over Q. So potential difference, which we usually just call voltage, or V, is just the work done, W, for each unit of charge, Q. It's all about energy per charge.
We measure this electric push in volts, named after Alessandro Volta, the guy who invented the first electric battery. And the definition makes total sense now, right? 1 volt is the potential difference you have when 1 joule of energy is used to move 1 coulomb of charge.
Okay, so let's recap. We have the flow, that's current, and we have the push, that's voltage. But how are they connected? Is there a predictable relationship between them? Well, a German physicist named Georg Ohm was really determined to figure that out.
So Ohm did this series of really simple but totally brilliant experiments. He'd set up a basic circuit and carefully measure both the voltage and the current. Then he'd add another battery, which doubled the voltage. And what do you think he found? The current also doubled. He kept doing this and saw the same pattern every time. For any given wire, the current was always directly proportional to the voltage. The ratio between them was always constant.
And check this out. Here's some data from an experiment just like his. See how as the voltage goes up, the current goes up in perfect lockstep. But now, look at that last column, V divided by I. It doesn't change. It's a constant, 15. This was the big breakthrough.
This discovery led him to formulate what we now all know as Ohm's law. He stated that the potential difference across a wire is directly proportional to the current flowing through it. It's simple, it's predictable, and it's incredibly powerful. Double the push, you double the flow.
And that proportional relationship gives us one of the most important equations in all of electronics. V equals I times R. We already know voltage and current. That new letter, R, well, that represents the constant ratio that Ohm found. He called it resistance. It's the property of a material that, resists the flow of charge. And we measure it in, you guessed it, ohms.
Now, this isn't just some abstract theory. Ohm's law is an incredibly practical tool we can use all the time to figure out how circuits are going to behave. So let's solve a quick problem straight from the source material and see it in action.
So here's our situation. We've got an electric heater. When we hook it up to a 60-volt source, it draws 4 amps of current. The big question is, if we take that exact same heater and connect it to a 120-volt source instead, what will the new current be?
Okay, let's walk through this using Ohm's law. First things first, we need to figure out the one thing about the heater that doesn't change, its resistance. We can just rearrange the formula to R equals V divided by I. So we plug in our first set of numbers, 60 volts divided by 4 amps. That gives us a resistance of 15 ohms. Great! Now we use that constant for our new situation. We're looking for the current, so we use I equals V divided by R. That's 120 volts divided by our 15 ohms, which gives us an answer of 8 amps. Just like Ohm predicted, we doubled the voltage and we got double the current.
So, to wrap it all up, here's your new toolkit for understanding circuits. You've got electric current, which is the flow. You've got potential difference, or voltage, which is the push. You've got resistance, which is the opposition to that flow. And then you have Ohm's law, the master rule that ties them all together.
It's pretty amazing when you stop and think that this one simple relationship, V equals I times R, is the absolute bedrock of all modern electronics. It governs everything from a tiny light bulb to a massive supercomputer. Which kind of leaves us with a final thought, right? How does this simple rule work when we start building bigger, more complex circuits? Well, that sounds like a great question for another time. Thanks for joining me.